All right. We have three sections left in chapter 4, and that will finish up all of our derivative rules. And moving on past this is just using them. So we're getting there. Today is focused on inverses, mostly on trig function inverses, but just also inverse functions, and kind of getting our introduction to that. And so that's kind of where we start our conversation, is just what are the basics of inverse functions. You have been introduced to inverse functions several times and in several different ways over the years. And part of that is, remember, an inverse function is kind of what undoes our function. If we were to do the composition of our inverse functions, we get the identity. But one of the major underlying concepts is taking your x and y in a point or in that function and flipping your x and y to get the inverse. So if a function has a point, a comma b, the inverse has the point, flip those around, b comma a. And that's kind of the underlying theme for everything, is your x's and y's will get flipped in the graph, in the equation, in all of that. So then kind of extending that all the way to our calculus, and what does that mean for things like a derivative of an inverse function and all of that as we look at flipping x's and y's. So this first part is just kind of reminding us about inverse functions and properties of them and all of that. And we're going to use the function that we know really well, f of x equals x squared, to kind of start that conversation. Now, later on in this problem, I ask us to specifically look at the derivative at x equals 3. And that's going to kind of impact how I start this one, because in order for this to actually have an inverse function, the domain would get restricted to one or the other half of that parabola. We're going to look at the positive half, because eventually I'm going to ask us to look at the derivative at x equals 3, which would be on the positive half of that parabola. So if we look at the graph of f of x, that is a parabola. We know some nice points on it. Again, I'm only going to look at the right half of it. So like 0, 0, if I plug in my x values, we're squaring them to get our points. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. And if we look at the inverse of that, there's kind of two different ways you can attack that. You can attack it algebraically, you can attack it graphically. If I were to attack it graphically, I would take each of those ordered pairs, so like 0, comma 0, and I would flip the x and y. Well, if I flip-flop x 0, comma 0, I still get 0, comma 0. 1, 1 is still 1, 1. But the point 2, comma 4 becomes 4, comma 2. And the point 3, 9 would become 9, comma 3. And we would see this picture taking shape. So a couple different things we can look at when we are talking about that. First of all, algebraically, what are we seeing happen? Well, to find an inverse algebraically, I take the equation, I, same as the points, flip my x's and y's, and I would solve for y. And again, because I use the positive side of this, we're going to use the positive side of our square root here, and we find the equation y equals the square root of x, which is that green line showing up right there. So you can see it then algebraically. Another way of thinking about inverses, flipping your x and y, is when we reflect something over the line y equals x. So if I were to reflect that over the line y equals x, you can see the inverse and the original function would match up with themselves. And same thing's going to happen with our derivatives of those, or the slope of the tangent lines, right, as we look at those. So now kind of taking this whole idea of inverses into our derivatives, or into our calculus world, looking at the tangent to the line at x equals 3, the derivative of our function at 3, we would be looking at this line right here, right? So if I were to look at the function and do that like algebraically, the derivative of our function would be 2x. And if I evaluate that at x equals 3, we would get 2 times 3, or 6, slope of 6. Okay? Now, here's what's tricky about doing derivatives when talking inverse functions. If I want to talk about the derivative that is associated with this one, I have to use its corresponding point, not the same x value, but its corresponding point. So remember that we flipped the x and y of this point to get this point over here, which is why when I look at the tangent line for the corresponding point, I'm going to look at the tangent line when x equals 9, because that's the corresponding point when I flip that point around. That was 3, 9 is now 9, 3. That's one of the hard parts on this one, is understanding why we're evaluating at different x values for those corresponding derivatives. Okay? But if we do that, this is our function, y equals the square root of x. And if I look at y prime, right, I'm going to rewrite it here as x to the 1/2. I would get 1/2 x to the negative 1/2, which would simplify into 1 over 2 square root of x. Good. And evaluating that at x equals 9, because that's the corresponding point in our inverse, I would get 1 over 2 square root of 9, square root of 9 being 3, times 2 is 1/6. Okay, now look at the two different derivatives that we got. I got a derivative with a slope of 6. I got a derivative that was a slope of 1/6. Do you think it's coincidence that those two numbers look related? If I'm asking you that, do you think it's coincidence? No, it's not coincidence. Guys, back up and think about what those are. Those are slopes, right? Slope, y2 minus y1 over x2 minus x1. If a slope formula is made up of x and y values, and moving from your function to your inverse, we flip all the x and y values, does it make sense that then this derivative, the slope, just turns upside down because all your x's went to the top and all your y's went to the bottom? Okay. Yes, it's true. That's exactly what's going to happen as we look at the derivative of the inverse at the corresponding point, is they are just reciprocals of each other because the x's and y's just flip-flop spots. Okay? But again, the hard part is understanding where that is located, because we did not plug the same x value into each of those to get those corresponding derivatives. There is a couple ways we can attack this. So one of those is using the formula. I like the formula. You don't have to use the formula. You can kind of work through it the way we just did, figuring out the corresponding point and thinking about reciprocal derivatives, which we will talk both ways on this problem. So it says the derivative, so now we've got a bunch of these little symbols up here. The derivative of the inverse is going to be this fraction, 1 over the derivative of the function evaluated at the inverse of that x value. Okay? So looking at an example here, we have some information given to us at the beginning. They tell us a little bit of information about our original function. The function at 5 is equal to 3. F of 5 is 3. They tell us the derivative at 5 is 2. We're supposed to find the derivative of the inverse of that function at x equals 3. So again, more than one way we can attack this, so I'm going to talk through it kind of two different ways here. The first way is just using that definition that we've got up here of our inverse derivative, and that is that I can do, actually let me back up here. Just remember that what this means is we have the ordered pair 5, 3 in our function, right? And that means that in our inverse, we have the point, flip-flop those, 3, 5, right? So as I go to use this, I'm supposed to look at 1 over the derivative of f of the inverse of 3. And I just figured that out. Our inverse is going to have a value of 5 at 3. So now I can replace this with 5. And they told us what that is. F prime of 5 is 2. Not always as easy to work through as this one, but could I have seen that from the original information given? Yes, if I can follow along again with what it's asking me and understand my corresponding points. They told me the derivative at 5 is 2. Well, the corresponding x in your inverse is 3. I get that information from here. So if the derivative there is 2, the derivative at 3 is going to be its reciprocal, 1/2. Okay? And again, what people struggle with is it's not the same x value, right? So understanding you're evaluating at corresponding x's for the function to its inverse. Questions on that section? All right. The rest of today we're going to spend talking about our inverse trig. Don't write this down, please. This is a little overwhelming. Your book has this, and I put this up here to show you that we can, in fact, these are not made up formulas that are in your notes that I'm about to give you for inverse trig functions. It's just quite overwhelming to look at the reason behind it, but it does go through finding the first one, and that would be the inverse of sine of x, okay, and the derivative of the function sine of x. So they go through the steps of how to find an inverse. Well, the steps to how to find an inverse, if this is my equation, if I want the inverse of that, I flip my x and y's, okay, which is what they show here. So sine of y equals x. And then they go through finding the derivative of that. So finding the derivative of that, they take the derivative of both sides. The derivative of sine of y and the derivative of x, both with respect to x. Well, the derivative of x with respect to x is just 1. Derivative of x is 1, right? On this side over here, remember this is your implicit differentiation, so they did chain rule. Derivative of sine is cosine, derivative of y is dy dx, or y prime, right? And they solve for y prime, dy dx, and get 1 over cosine y. And then they talk about all this stuff where they justify the fact that can be in the denominator because it's going to be a non-zero, and that it's actually going to be positive. And then this part they just kind of throw in there and kind of expect you to understand what's going on, is that they replace cosine of y with this thing, and that seems so out of left field, okay? So let me clue you in on where left field is. Left field is your Pythagorean identities. They took the cosine squared, sine squared plus cosine squared equals 1, solved it for cosine, except for they did y's instead of x's, okay? That's what it would be if we solved it for cosine. And they replaced cosine with that. They also replaced sine of y with x, getting us to the formula here. You don't need to know that. It's true. We can prove that for all of our trig, inverse trig formulas that you're about to get on the next page. I just want you to know that there is a reason behind them. They are not just random, but not worth our time to really go through deriving all of these. We could, but it'd be pretty overwhelming. We need to just be able to use these. So you're going to want to have this table in your notes. There are, well, 2/3 of them that we will memorize. The other 3 we will not. I'll give you a minute to just get that into your notes, and then we will talk here in a second. All right. Of these up here, the ones that we are going to want to know would be our inverse sine derivative, our inverse tangent derivative, and our inverse cosine derivative. The others you need to know how to use but not have memorized. Of that, I want to point out there really is only 3 on the board. And if you look at the column on the right, it completely just repeats the column on the left, except for it's got a negative in front of each one. So if you can remember which one it's related to, we really only need to memorize 2 of them, because sine and cosine are the same setup. The only difference is cosine has a negative in front of it, and sine does not. So if you know that, if you know inverse sine derivative, you know inverse cosine derivative. Kind of easy because these are the same that have negatives when you do their derivative when it's not inverse, and they're also the ones that have negatives on the inverse derivatives. So kind of help you with some of that. And the other note I have at the bottom is usually we have to use our chain rule. So when I'm doing this, right now these would all be plain x's on the inside of these functions. But as soon as I put this as something more than just a plain x, when I set this up, this part right here is just holding the place for the inside function. And then we would follow that with the derivative of the inside function, just like chain rule says. Derivative of the outside function times the derivative of the inside function. Okay, so when we set this up for chain rule, whatever's written here goes wherever x squared is and would get squared by this formula, which we're going to look at some examples here at the beginning to kind of do some basic ones of just seeing the chain rule in action here. So I've got 2 problems on this page. We'll start with that first one. It asks us to do the derivative of the inverse sine of 3x. Okay, so our outer function, remember we always have these layers going on. Our outer function is inverse sine, and our inner function is 3x. So we start with the derivative of the outer function, which is that formula up there, 1 over the square root of 1 minus our insides squared. And our insides is 3x times the derivative of our insides. Chain rule, right? So the derivative then of 3x would be 3. Now, when I am cleaning this up algebraically, remember that 3 is a fraction as well, 3 over 1, and we multiply fractions straight across the top, straight across the bottom. So when I multiply this straight across the top, straight across the bottom, 1 times 3 is 3. Cleaning up the bottom here, when I have a monomial squared, that ends up by squaring both parts here, so 1 minus 9x squared. My last little note algebraically, and I know none of us would ever do this, but can I square root the 1 and the 9? They're both perfect squares. It's a subtraction. Say no. No, I cannot do that, right? Not a legal maneuver. You cannot just go through and square root perfect squares throughout there if there's a plus or a minus in there. We would have to have factored that and gotten the same thing in 2 parentheses, which that does not factor into the same thing in both parentheses, right? So that is as simplified as that's going to get. You are done. Questions? What's that? You do not, actually. In calculus, you'll almost never see them rationalize. Why we spent so many years then rationalizing? I don't know, but it's kind of nice that we don't have to anymore, right? So, yes, you could. It wouldn't be wrong. We don't need to. All right, let's do the second one. Derivative of inverse sine of x squared. So again, just a basic chain rule one here. Outside function being inverse sine, inverse function being x squared. So again, there's our setup for the derivative of inverse sine, holding the place for that inside function being x squared, times the derivative of our inside function, which would be 2x. And then cleaning that up, I can multiply straight across the top, straight across the bottom. 2x would be in the top times 1 over 1 minus x squared squared is x to the 4th. Can I square root both of those? Say no. No, I cannot. Okay, good. Any questions on your basics? All right. Pretty much how we follow all the rest of them. I do have one that has a little algebraic trick to it, this guy, that we will see super rarely, but it's worth talking about real quick. Go ahead and try setting this one up. And then I'm going to talk about, in the simplifying process on this one, the tiny little trick that we need to address that is true, we just don't ever really see it. Okay, the secant derivative, inverse derivative, has two places that our insides go. We have that absolute value sitting at the front, and then it shows up again inside our radical squared. So our insides are 5x to the fourth, and then our insides is a function more than just a plain x, so I'm going to need to follow this up by multiplying by the derivative of the inside. So 4 times 5 would be 20, subtract 1 from that exponent, so 20x to the third. Okay. Similarly to what we were doing before, multiply straight across the top, straight across the bottom. Go ahead and square both parts there, so 25x to the 8th. Minus 1, still can't simplify that, right? It's still got a plus or a minus in it, so it's going to sit as is. Now, normally I would tell you that we would be done at this point. We can't simplify because it's got that, well, nothing for the radical. We've got that absolute value thing going on the bottom, okay? But the whole purpose of an absolute value is to guarantee that you're getting what type of an answer? Positive, okay? Well, if it's 5x to the fourth, what kind of answer are you going to get already? Positive. So isn't it kind of redundant that we have gonna be a positive number inside of absolute value symbols? Because I can already guarantee you this is positive. 5's a positive number. X to the fourth is something positive because it's an even exponent. This has to be positive. I don't need the absolute value bars. Well, in that situation, what has to be true for this conversation to happen? An even exponent. If that's an odd exponent, this is not a conversation, right? But if it's an even exponent, it is, because then I don't need those absolute value bars. Well, as soon as I drop those absolute value bars, can I simplify further? Yeah. Okay. You wouldn't see probably that answer in a multiple choice option. You would see the simplified version of it, and that's where I can simplify 20 and 5, both divisible by 5. X to the fourth, x to the third, I can take an x to the third out of each of those, right? Leaving me overall with 4 over x square root of 25x to the 8th minus 1. And it would be pretty confusing if that's what I was looking at and that was the option in my multiple choice line, right? Again, if that changes to an odd exponent, those bars don't go away, and this is as simplified as it gets. So it's that rare case. Questions on that? Always good to kind of refresh and talk algebra stuff. Okay, then moving on from that, there are some times that we will want to type this into our calculator. But I do want to clarify, I don't have a cosecant, a secant, or a cotangent button on my calculator. In pre-calc, if I wanted to type into my calculator the cosecant of pi over 3, and I wanted a decimal answer for that, I wanted to type it in my calculator, I would have had to type in its reciprocal, 1 over sine of pi over 3, right? Inverse functions don't work that way. I can't just put it in the bottom of the denominator. So the reciprocal is actually happening here inside of your function. And so notice on secant and cosecant, if I'm trying to do the inverse of those, this is actually what I would type into my calculator. Your inverse being the button above cosine, sine, and tangent, where it's raised to the -1. Cotangent, because of where inverse functions are defined, are a little bit different. You have to do pi over 2 minus inverse tangent of x for that one. And again, this is only if I want to type it in my calculator. And I'm going to talk to you on the next example about when we could, but don't have to necessarily, if I remember my inverse trig, type this into our calculator. And those conversions would be needed for that. Again, not something we need to memorize, but kind of understand what's happening with that and why, that we can't just type it in 1 over the other function, okay? These are all on the next page, so you guys can keep writing. They're all over there still. So looking at a situation where we could utilize a calculator conversion, it says find an equation for the line tangent to the graph of y equals the inverse cotangent of x at x equals -1. Now, you actually can get through this problem completely without using my calculator, but we'll talk about calculator versus non-calculator on this, okay? But guys, it's asking us for the equation of the tangent line. The process for that will never change. We needed 2 things for an equation. We need the point, we need the slope. The point comes from the function, the slope comes from the derivative. That will be a consistent conversation this entire year. That's never going to change. So when they ask us for the equation of the tangent line, I need a point that comes from my function. I need a slope that comes from my derivative. They do ask us to do this at x equals -1. Okay. Now, I'm supposed to be finding the y value by plugging -1 into my calculator. And evaluating this at x equals -1, but we don't have this option. This is where we could use our calculator conversion. So my calculator conversion says that inverse cotangent of x, when I want to type it in my calculator, is actually going to be pi over 2 minus the inverse tangent of x at x equals -1. Now, I believe it is if you are a physics person, you're going to need to remember that in here, when we are using our calculators, we're always in radians mode. And I believe in physics, you're in degree mode. So just make sure that you guys are making the switch back and forth. And it only matters if you are hitting the button sine, cosine, or tangent. But let's go ahead and grab our calculators and see what we get when we type that into our calculator. Pi over 2 minus inverse tangent of -1. Make sure we all know where those buttons are located. And it comes out to something ugly, 2 point something, something, something. 2 point, who's got that figured out? What is it? 356. Okay. Remind me to come back and talk about that part of it at the end here, but also just make sure you know how to type that into your calculator. Okay. The slope, so there's our point. The slope part of it, we have to find our derivative. So I want the derivative of inverse cotangent, and inverse cotangent's derivative is -1 over 1 plus x squared. And we want that to be evaluated at, and again, I don't have to memorize that, I'm just going to go grab that off of my table, right? I'm going to go evaluate that at x equals -1. I'm going to be a really good algebra student right now and remember that when I plug in a -1 to be squared, it comes out positive. Yeah? So 1 plus 1 is 2, and I find out the slope of this is -1/2. Last step is just writing that into my equation. So y minus 2.356 equals -1/2 x minus -1. Questions on any of that? Okay. Now, if I were to really challenge you, I might have taken away your calculator and said, figure this out without your calculator. And you can, It just requires that we remember our pre-calc and our inverse trig on the unit circle. If I was looking for evaluating the inverse tangent of -1, not 0. Tangent is 1 at what angle? Pi over 4. So the inverse tangent of that, now, inverse tangent of a -1 is actually down in quadrant 4. It would be a negative pi over 4. This would end up being pi over 2 minus negative pi over 4. 1/2 time plus a fourth is 3/4. And we get 3 pi over 4. If you type 3 pi over 4 into your calculator, it comes out to 2.356, blah, 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 blah. You really could have done this with a calculator, assuming we remember our unit circle and inverse trig and all of that pretty well. Probably not going to have to remember that without our calculators, though. So I could have seen this, and this would have said instead y minus 3 pi over 4 equals -1/2 x plus 1. Questions? All right. Last thing. Particle moving along the x-axis. Remember, it doesn't leave our x-axis. It just slides left and right the whole time, right? Particle moving along our x-axis. So this position at any time is greater than or equal to 0. Isn't time always greater than or equal to 0, right? We're not going to have negative times ever. Gives us a position function of x of t equals inverse tangent of square root of t. What is the velocity of the particle when time equals 16? So that last part is the question. What is the velocity of the particle when time equals 16? I can read that in different words. Instead of saying what is the velocity of the particle, I can read it as find the derivative and evaluate at 16. Right? Isn't that the difference from going from position to velocity is just the first derivative? So that's what it's asking us to do. What is the derivative of the particle at 16? So that's exactly what we're going to look at. And this is, again, just using our inverse trig derivatives that we just wrote down in our notes today. One thing I might want to do is help my algebra brain out here and rewrite that as t raised to the 1/2, because we're going to have to take the derivative of the inside of that function as well. So the derivative of our position function is equal to our velocity function. It is a chain rule problem, so I'm going to do the derivative of the outside function, which is inverse tangent. Derivative of inverse tangent, 1 over 1 plus the insides squared. Our insides are the square root of t, or t raised to the 1/2. Chain rule, so now times the derivative of the inside. Derivative of t raised to the 1/2 would be 1/2 t raised to the -1/2. Now, if I was just finding the derivative, cleaning all of that up, first of all, square root of t squared is t, right? This could be rewritten, move that down to the denominator because of the negative, make it back into a radical because of the 1/2. Put it all together. Looks something like that. 1 over 2 square root of t times 1 plus t. Velocity. Evaluated now at time equals 16. Plug that 16 into all of the places that there is a t. 2 times 4 is 8. 1 plus 16 is 17. And then I'm going to grab my calculator because I don't know what 8 times 17 is. And you guys are going to tell me, what is it? 136. Questions? All right. Your assignment, a bunch of random problems out of the book, 1 through 5, 9 through 12, 24 through 27, and 37 through 40.